All right, everybody. First, I want to say it was really nice seeing everyone this week. I'm working on your tests. It's going to take a little while because it's pretty hard to grade them this way, but they hopefully will be posted by Saturday. This is just something that I found online. I don't have it posted under note packets. I don't know if you've noticed that, but I made a new content area in Blackboard. It's called Note Packets. So if you want to download the notes, you can. You don't have to if you don't have a printer. It's not a big deal. You could just follow along with the notes I'm going to do in class. Right? You can just follow. When I say in class, I mean like the notes I'm making here. You can just get some notebook paper and follow along. But I did not post this. I thought this was just something interesting that I saw online that a friend had sent me. So he had done, this is what he's teaching right now, and he was showing me that he called this the old school way, and I know you can't read it, but this says, what is this, where did this zero come from? Like he said, he gets these questions, and he said that his students get confused, like when they put the two numbers up there, they get confused with the numbers if they don't cross them off. But he said this is the number sense way. He called it number sense, but it's the Common Core. He crossed that off and said it's really a lot of number sense that they're teaching. And so they're taking this multiplication problem and doing the area model. And so what they're saying is that 97 is 100 minus 3. Isn't that what 97 is? And 98 is 100 minus 2. And then they're just doing the multiplication like I showed you. So you can see the boxes. Okay? And then, so this is 100,000 minus 500. I say 100,000. 10,000 minus 500. So there's the 9,500 plus 6. So it's kind of cool. I was like, oh, and it works for any numbers that you want to, if you want, especially if they're like close to 100. I think this was convenient because we could make two 100s out of it, and so that's easy for kids to multiply. It was just one and then add the zeros. But I was like, oh, that's really cool. So I just thought I'd share that with you. And then we ended the last lecture with practice finding prime numbers, and so I thought, oh, well, let's just pick some more numbers and we'll find the primes. This a type of problem like this is on your Oh Wow this week. Our last Oh Wow, actually. So let's practice this again. So if you remember, on the sieve of Aristophanes, we circled the 2, the first prime number, and then we crossed off all multiples of 2. So any even number is a multiple of 2. So all of these numbers cannot be prime because they have a factor of 2. And a number is prime if it has exactly 2 factors, 1 and itself. So since these have 2 as a factor, they have more than 2 factors. All right. Then we circled 3, and then we crossed off all multiples of 3. So we know if these are multiples of 3, if the sum of its digits adds up to a number that 3 will go into. So let's see. This adds up to 8, so we can't cross off that. This adds up to 10, can't cross off that. This adds up to 12, and 12 is divisible by 3, so we can cross that off and then go every third. 1, 2, cross off. 1, 2, cross off. Right, that adds up to 9. So those digits add up to 9, so that's good that we cross it off. 1, 2, cross off. 1, 2, cross off. Let's check. So the digits add up to 15, and 15 is divisible by 3. And then we already crossed off 4, so then we circled 5. We cross off all multiples of 5, and we know if it's a multiple of 5 if it ends with a 5 or ends with a 0. And then we crossed off, then we circled 7, and then we're going to cross off all multiples of 7. So that's when I'm pulling out my calculator. But look, we only have 1, 2, 3, 4, 5, 6 left. So this really isn't going to be terrible. So let's see if any of these are divisible by 7, or let's see if they're multiples of 7. It's saying the same thing. 523 divided by 7. Nope. 527 divided by 7. Nope. 529 divided by 7. Nope. 533 divided by 7. And 539 divided by 7. Nope, we hit one. There we go. So we get to cross this one off, 539, because that is divisible by 7. So 7 is a factor. All right. And then the next prime number, well, 8's not prime, 9's not prime, 10's not prime. We circled 11. Okay? So remember, on the chart, the first one we would look at is 11 times 11 and cross off 121. And then all other multiples. So let's see if any of these are divisible by 11. Oops. 523 divided by 11. Nope. 527 divided by 11. 529 divided by 11. 533 divided by 11. Okay, so it doesn't look like anything that's left is divided by, or divisible by 11. So let's try 11, 13. So 521. Now here, first, let's do 13 times 13 is 169. So we're still on the chart, because that would be the first number I cross off on the chart if we had a chart that went from 1 to 539. All right, so 521 divided by 13. Nope. 523 divided by 13. 527 divided by 13. 529 divided by 13. 533 divided by 13. Oh, there you go. That one's off. That one is not prime. So now we're down to 4. So let's see. The next prime number is 17. 17 times 17 is 289. So that's where I would start in my chart. All right. So let's see. 521 divided by 17. 523 divided by 17. 527 divided by 17. Oh, there we go. We got another one. So let's cross off 527. It's divisible by 17. All right, and then the next prime number is 19. Are we still on the chart? Yep, still on the chart. So that would be the first one we'd cross off, and then we got to see if there's anything left that are multiples of 19. Nope. Nope. Okay. Let's see. The next prime number is 23. Oh, look, we're on the chart, and that would be the first thing that we'd cross off. So we'd cross off 529, and then we'd cross off all multiples of 23 after that. So do you see, as soon as you're off the chart, like right now, we're off the chart, the only numbers that you have left are prime. So those two numbers have got to be prime numbers. The key thing is to know when to stop. So now I don't need to go to 29, because the first numbers I would cross off are 29 times 29, and that's off the chart. I'm hoping that makes sense. Like, that's important to know, like, when do we get to stop? So you stop when the product of that prime number times itself is off the chart. So then you know you've exhausted all of the possible prime numbers. All right, so that is that. So this section is in your note packet. It's in the note packet on Blackboard. It's long. It's like 17 pages, and then I printed off. I made another one today to go with it. You don't have to print these off, right? You could just take notebook paper and just take some notes, okay? So I would go get some notebook paper if you need it. And I'm just going to start working through some material on fractions, all right? So the title of the section is Fractions, and I put and rational numbers, because it's important to understand the difference between a fraction and a rational number. So technically, kids really talk about rational numbers. Right, is really a better way to express it. I mean, fractions are fine, and that's what everyone says, but let's look at the difference between those. A rational number is a number whose value can be expressed as a quotient or ratio of two integers, where A and B, integers A and B, represented as A over B, where B can't be 0. And we talked about that. You're not allowed to divide by 0. So two integers, like 3 over 5 or negative 7 over 2, right? Those are what are called rational numbers. And we'll talk about the density in a little bit, that between any two rational numbers, you can always find another rational number. That's an interesting little fact. But a fraction is interesting. So a fraction is a very specific, well, let's look at it. A fraction says a number whose value can be expressed as a quotient or ratio of any two numbers, A and B, anything. They can be anything that they want, represented as A over B, where B can't be 0. So, for example, pi over 6 is a fraction, but not a rational number. So when we're talking about elementary school, we're pretty much limiting ourselves to rational numbers. So fraction is a much larger body, but we're really only talking about rational numbers, which is a little part of fractions. I'm hoping that makes sense. Like, fractions is a really broad term. Most elementary schools don't talk about pi over 6, right? Or square root of 2 over 5. That is a fraction, but it's not a rational number. So rational numbers are just integers over integers. Okay? All right. But anyway, what's the fancy word for A? A is called the numerator, and B is called the denominator. Now, I was always taught that B is the number of parts a whole has been divided up into, and A is the number of parts of interest. It's a little bit different with the Common Core and how they define it. So I was always thought B is the number of parts a whole has been divided into, and A is the number of parts of interest. So 3 over 5 would mean I have a whole that's been divided up into 5 parts, and 3 of them are shaded. 3 are what I'm interested in. So numerator and denominator. Numerator is the number of parts of interest, that's what I was taught, and B is the number of parts a whole has been divided into. Very interesting about Common Core and Engage New York. So Common Core starts fractions in 3rd grade, and so I looked at some very, very beginning 3rd grade sheets. So 3rd grade is where it's at. And I think this is interesting. So they talk about a fraction A over B as the quantity formed by A parts of size 1 over B. So they don't say like the whole has been divided up into B parts. They say that the whole has 1 over B as one of its slices, and we're looking at A slices. It's interesting. So they're talking about the value of a slice, not how many parts it's been divided up into. So like, so if we talked about 3 over 5, Engage New York would say we have 3 of the parts 1/5. Do you see the difference? Like, I would have said a whole has been divided up into 5 parts and we want 3 of them. They would say we have 3 of these parts of a whole that are each a value of 1 over 5. It's different, but it's cool. It's different. And so here they talked about the set of fractions not only includes rational numbers like this, as the standard applies, but fractions also include numbers like this. So they're making the discrepancy, right, for us, that we're really looking at rational numbers, because fractions have these numbers that we really don't include in elementary school. All right, but anyway, let's just take a peek at some 3rd grade work, okay? Just take a little peek at it. It says, estimate to draw lines to show how you would cut the paper into fractional units as indicated below. So halves, fourths, eighths. So they're having kids, different ways to draw something into 4 equal parts, right? You can go up or down or make a big plus in the middle. So that's the very beginning of fractions in 3rd grade. And then I just think it's interesting. This was kind of cool because a lot of elementary school kids will say, oh, you divided a shape into 3 parts and you want to shade one of them. But the key thing, right, all 3 of these describe that. But the key thing is, right, they all have to be equal parts. So that's an interesting little lesson. This is cool because it gets kids to understand the bearings of what the whole is. So it says this whole shape represents one whole. Okay, and then it says write a unit fraction to describe the shaded part. So this would be 1/2. So this represents 1, this whole thing, and then the shaded part represents 1/2. Now over here it says the shaded part represents a whole. So this is what 1 is. And they say divide 1 to show the same unit fraction that you wrote in part A. So we want to divide this into 2 equal parts, and that would be 1/2. So they're getting kids to see that it just depends on how you orient yourself. So, for example, if this is a whole, then this is equal to 1/4. But now they're saying this little guy is the whole. So to represent 1/4 on this, we divide it up into 4 equal parts and shade in one of them. So this is a really good exercise to have kids start getting their bearings on what a whole is, right? It's a really cool exercise. So, for example, this would be 1/3. So to represent 1/3 on this, unless you want to go this way, I'm going to go like this, and then this is what 1/3 would be. So you have to get oriented to what the whole is in order to understand how to break it into parts. I just thought that was really, really a clever little exercise. The directions at first, I'm not going to lie, were a little confusing. And then this I thought was also interesting because it's this unit fraction that Engage New York is focused on, this unit fraction. So here's a sample. They have a circle. There's 4 parts. The total number of shaded parts is 3. So each part is 1/4, and they would say that we have 3 of these 1/4. Okay? So 1, 2, 3, 4, 5, 6, 7, 8, 2, 4, 6, 8, 9. I hope I counted that right. 2, 4, 6, 8, 9. So you've got 9 equal parts. 1, 2, 3, 4. 5 of them have been shaded. Each little piece is worth 1/9, and they would say we have 5 of them. So we have 5 of these ninths. And I'm going to show you this in the directions that they have for another worksheet. It's really interesting. All right, I think you probably got the hang of it. And then, of course, Engage New York loves their number bonds, right? So we're still in the same module of 3rd grade. So it says, show a number bond represented what is shaded and unshaded in each of the figures. And then they have them draw another visual that would represent the same number bond. But this is cool because they're going to use this later. They're going to use this later with mixed numbers and proper and improper fractions. So I like it though because they start off with the 1 always, and then they break it apart. So we would have 2/5 unshaded, or did they want, doesn't matter, shaded to unshaded, I guess it doesn't matter, and then 3/5 shaded, or you could flip it around if they were really picky and they wanted the 3/5 shaded to the 2/5 unshaded. But it's cool because guess what? Then this is how they're going to teach them how to add these, right? that to get to 1, we're not adding the denominators. We keep the numerators, we keep the denominator and add the numerators. And then they're going to talk about how that's 5 over 5. It's very interesting, but they love their number bonds. And the reason why they number bond these is so that kids eventually can see that when you add to get 1, you would add the numerators, keep the denominator. I don't know, I just think this stuff is cool. And then they just had a whole worksheet on it. So that's 3rd grade. I've actually had some friends contact me about the Engage New York 5th grade questions, and so I thought, oh, this is really good that you're asking me this, because I'm going to include it on my sheets for my students. So these were both, this was a friend, Melissa, that just called me, and this was an Engage New York question from a little ways back, but I thought, because everyone's homeschooling now, so people have been calling me for help. So I thought, I'll put this was a couple weeks ago, I'm going to put this on too. So it says, these are 5th grade though. It says, Josh is going through a large bag of balloons containing red and blue. He finds that 1/8 of them are blue. He also notes that there are 120 more red balloons than blue. So how many blue balloons are in the bag? All right. This was tricky because they're not doing algebra. You can't let x equal something. So I was telling my friend, you've got to draw a picture with it. So I'm just going to draw it as a rectangle because Engage New York loves their tape diagrams. All right, so this is going to be my bag of balloons. Some are red and some are blue. And he finds that 1/8 of them are blue. So if you call this 1/8, everything gets divided up into eighths, right? That's an Engage New York. If one thing gets split up, the whole thing gets split up. So we're going to divide this whole thing into eighths. Okay? And he notices that 1/8 of them are blue. So these are the blue ones. The rest of them are going to be red. All right? Now here's the key thing for this. You ready? So I'm going to put some quarters up here. And I'm going to put some pennies. And I'm going to ask you guys, boy, I wish we were together for this. I'm going to ask you, how many more pennies are there than quarters? Now that would seem like it's a very easy question. You would say there's 2 more, right? Because this is where they're the same. This is a 1-to-1, and then we have 2 extra. So you would say 2 more. Do you see, like I set these aside because this is where these are the same, and then these are my extras. All right, let me put down another quarter. I said, okay, how many more pennies do we have than quarters? Well, we all can just look at that and say, oh, there's 1 extra penny. But this is how you want to think about it. Look, there's 3 quarters. So these are where they're equal. This is where there's the same number of pennies as there are quarters. And then you have 1 extra. Okay, you might have to watch that a couple times to get what I'm talking about, because this is what it's saying. There are 120 more red balloons than blue. So that means this is where the 2 of them are equal. And then these ones would equal 120 balloons. He said there are 120 more reds than blues. So they lined up the reds and the blues and said, okay, so here, let's pretend these are the balloons. So these are the blue, these are the reds. The quarters are the blue. So they lined them up and said, here, I'll do it this way, because that's how my box looks. So these are the blue, these are the reds. They said, okay, well, more reds than blues. So they lined up the reds and blues and said, okay, this is where they're equal, like this. This is where they're equal. This is where the red and the blue are equal. And then the leftovers is going to equal 120. Okay? So then it says, how many blue balloons are in the bag? Well, these are all, same number of balloons are in each of these little columns that I made. So what's in each column? Well, 1, 2, 3, 4, 5, 6 equals 120. So there's got to be 20 in you, 20 balloons in you, 20 balloons in you, 20 in you, 20 in you, 20 in you, 20 in you, and 20 in you. So there you go. There's 20 blue balloons. interesting fraction question, right? That's interesting. All right, let's look at the other 5th grade one. So 3 rectangular prisms. A rectangular prism is a shoebox. That's what a rectangular prism looks like. It's just a shoebox. A prism is a 3-dimensional shape, and the rectangular part is the shape of its lid. So it's a rectangular prism, has a combined volume of 518. So 3 of them have a combined volume of 518 cubic feet. Prism A has 1/3 the volume of Prism B, and Prism B and Prism C have equal volume. Okay, so I'm going to draw, here's B, here's my shoebox for B, okay, and here's my shoebox for C, and they say B and C have equal volume. Okay, so A is 1/3 of that. Does that make sense? But look, this is not, it's all about dividing among equally. So if this is 1/3, to try to get oriented, that would be, that's kind of what that looks like. So there's A, this is B, because it's 1/3. Prism A is 1/3, and then let's divide, everything gets the same size. Like you could stick them together and they would all be divided up equally. So if we add these 7 pieces, they add up to 518. So what's 518 divided by 7? Looks like 74. So each of these pieces are going to have the same volume. You get 74, 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 and you get 74. So what's the volume of each prism? Well, this is A. 74 times 3. I don't know what I'm doing there. 74 times 3 is 12, 21, 22. So then you are, so this is B, so it would be 222 cubic feet, and you get the same, 222 cubic feet. Okay? So anyway, I just thought those were interesting questions. Definitely a little different, harder, that's why parents were calling me, but it's all about this concept of Engage New York where everything gets divided equally, and we're going to see that in a second with improper fractions to mixed numbers. All right, so let's just get down some terms that you have to know with these different types of fractions. So a proper fraction is a fraction whose value is between 0 and 1. Right? So if you've got a proper fraction, then doesn't it make sense the numerator's got to be smaller than the denominator, right? So this is a fraction whose value is less than 1 but greater than 0, so the numerator is smaller than the denominator. A mixed number is a whole number and then a fractional component, and typically that fractional component is an improper fraction. So you've got a whole number plus a proper fraction. Whole number, proper. And then improper is where the numerator typically is bigger than the denominator. So its value is going to be bigger than 1. They say, I mean, technically this is also improper because they say it's at least as large as the denominator, but technically an improper fraction is a fraction whose value is 1 or larger. The numerator, with identity's sake, I always say the numerator is going to be bigger than the denominator. Okay? All right. So those are 3 terms you have to get down because we're going to be using them throughout the rest of the remainder of the course. All right, very different on how they're teaching kids to go back and forth between improper fractions and mixed numbers. So I thought, so this is going to be something on your test. I want you to do this Engage New York style, right? So here's the directions, the teacher and the student. So it says, model with a number line to convert the mixed number into a fraction greater than 1. So we're going to do it on a number line down here, but we're going to also do it with number bonds. So 2 1/6. Use a number bond to decompose 2 1/6 into ones and sixths. So do you see the first thing they did is broke it down into its whole number and its proper fraction. And then they said, well, how many sixths are in 2 ones? And they said there are 12 sixths. So do you see they crossed this off and said there are 12 sixths in 2 ones. And then they add these together. So 12 6 and 1/6 is 13/6. I think that's very different and very cool. All right, we're going to look at it again in a second. Let's try this one. All right, use a number line to model your work. Okay, so I'm going to play it out for you how the directions said in the little teachers thing. So it's 3/4. So they have the kids go 1, 2, 3, 4, and then the 1, 2, 3, 4, and then we're going to divide this into 4 equal parts because we have to get a fourth. So right here is the 3 1/4. But look, if this gets divided up into fourths, everything gets divided up into fourths. It's only fair. And then they just count the fourths. So we're going to stop right here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13/4. Right? From here to here there was 12 of these fourths, and then another one. Will it give us 13/4? What? Very different. Very, very different. So this is actually 4th grade. Okay, we're just trying to give you a little flavor of everything. So here, I'm going to do it again, and so you can look at the teacher directions. You ready? So they want to take this, we're going to do it, but in the other direction, right? So now we're going to write this as this improper fraction as a mixed number. Okay, so let's follow the directions. All right. It says write 4/3 and say the fractions. So the teacher would say this is 4/3. Oh, the students are supposed to say 4/3. Okay. They say draw a number bond because they love their number bonds with 4/3 as the whole. Draw a number bond with 4/3 as the whole. So they say how many thirds are in 1? So they say you could, well, there's 4/3 altogether, but we can get 3. Oh, here. Write 3/3 as a part. So they say write 3 in the bottom, and then it says write the remaining part, fill in the unknown numerator. So they're having the kids do that. So anyway, so we can get a full 3/3, and then they said, okay, what's left over? Then there's a 1/3 as the unknown part that's left over. And so cross this off and make a 1. Right? There it is. So 4/3 is 1 and 1/3. Very different. All right. And then you can also do this with the number line. Okay? You can also do this with the number line. So I'm going to reenact it for you. Ready? Okay. So here's my 0. We're going to draw out 11 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's my 11/3. But every time I go 3, that's going to, because 3 says that's going to be what a whole is worth. 1, 2, 3, there's 1. 1, 2, 3, there's 2. 1, 2, 3, there's 3. So this is 9/3, which is 3, and then we have another 2/3. So it's 3 2/3. I've never seen this done before, Engage New York. I thought this was very, very different. Very different. So this kind of stuff will be on the part 2 of your test where you get to pick and choose. I thought these were very interesting techniques. So what I want to get done, because obviously we're not going to cover all of this, is I want to just start getting through some of the comparing fractions, and then we'll finish that on Tuesday, okay? And that you should definitely have everything you need to get through the Oh Wow. So you can do some of the Oh Wow, but most of it, quite a bit of it is the stuff we're going to talk about on Tuesday, but we can at least get it started. Of course, I don't have my fraction circles. They're up the college, but I think we could probably draw these out. It's really easy to do with fraction circles if we had the actual manipulative. Right, so this is what 1/2 would look like. And if we divided this up into 6 equal parts, and we had to shade in 3 of them, right, you can see that you're going to get half the circle again. So it's easy for kids, especially if you have these manipulatives, to play with these so that they can see the idea of what an equivalent fraction is. Let's see, 4. Let's do it this way. Okay, so 3 out of 4 would look like this. If I had to do 6 out of 8, there's 2, 4, and then I'll do these 2 at the top so you can see that it's similar. And then just something aside, and this is just a little fact that I thought I'd throw at you. If you want to make a really quick test to see if fractions are equivalent, their cross products are the same. So 6 equals 6, 24 equals 24. I just thought it was kind of cool. So cross products are equal. For equivalent fractions. So this is hard, I think. I mean, my kids love doing fractions. They thought it was fun. But it is a little different, right? I mean, these don't look anything alike, but so the fact that they represent the same value is kind of interesting, right? Definitely something new for kids when they're starting this in 3rd grade. But it's important for them to be able to make equivalent fractions. So if we start off with something like 1/3, to make an equivalent fraction, and they get into this in a lot of detail, they multiply. This is 3rd grade, I think it's the end, because that's when they start multiplication. They can multiply, just pick a number. This is where I would ask someone, give me a number. And if you said 5, we would just take the numerator and denominator and multiply both by 5, and we'd make an equivalent fraction. Right? If someone in class said 2, we'd multiply the numerator and denominator by 2, and then we would make an equivalent fraction. Right? So to make an equivalent fraction, you just multiply by 1, where 1 is in disguise, right? Because that's the only way you can multiply a number without changing it, is multiplying it by 1. All right? Okay, so let's get into some of the good stuff here with comparing fractions. This is some pretty big, very different stuff. So everything you see here I pulled off of Engage New York, okay? Sometimes I cut off the title. All right, so this is all in 4th grade. So all of these examples I pulled off of 4th grade work, okay? So you'll notice, and I made a little mistake. That should be a 3/4 up at the top. That should be a 3/4. So you notice that the first 9 problems, either the numerators are the same or either the denominators are the same, okay? So for this one, either the numerators are the same or the denominators are the same. All right. If the denominators are the same, it's really easy. If we had our fraction circles and our manipulatives, it's really easy to see that 3 pieces that are worth a fourth is more than 1/4. So if the denominators are the same, these kids have these manipulatives that they can pull out. You're just comparing the numerators, right? So if the denominators are the same, you're only comparing the numerators, and the bigger the numerator, the bigger the value of that fraction. So if you need to write that down, you can. If the denominators are the same, you're just comparing the numerators. If the numerators are the same, do you see all these? Then you need to look at the denominators. Now listen, it's very easy for kids to figure this out, especially with the unit fractions that Engage New York talks about. They're going to see very quickly that the bigger the denominator, the smaller the piece. So 1 piece out of 4 is going to be much smaller than 1 piece out of 2. So they're going to get this very easy, especially because the fractional circle set that my kids had went up to 13. So they had circles that were divided up into 12 that you could break apart, and circle fractions that had 13 pieces in them. I'm trying to think if there was more than that. But anyway, so they have these. They can see that 1/5 is much bigger than 1/12. They would be able to see that 1/25 is much bigger than 1/34, especially when they have these manipulatives in front of them. So whether it's 1 or 2 or 5 or 6, as long as the numerators are the same, they look at the denominators. The bigger the denominator, the more pieces the pie has been cut up into, so the smaller the piece. The bigger the denominator, the smaller the pieces. So 5 of these teeny pieces is going to be smaller than 5 of the larger pieces. Right? The bigger the denominator, the smaller the piece. So I'm going to write that down in the little note section. All right? The larger the denominator, the smaller the unit fraction. Right? The larger the denominator, the smaller the unit fraction is, or the smaller the piece size. The smaller the piece of pizza. If you're cutting up a pizza into 20 slices, man, those slices are going to be small compared to if you cut up the pizza into 5 slices. Same pizza, right? And I like how they're using the words too. Like compare 1/3 to 1/5, right? So 1/3 is going to be bigger than 1/5. Or compare 1/6 to 1/6. They're getting these kids really comfortable saying these fractions. Or 1/16 to 1/16 compared to 1/11, right? The larger the denominator, the smaller the piece. Okay? So I thought those were interesting. I thought those were kind of interesting. The kind of intro to comparing some fractions. So let's look at this part. So Engage New York in 4th grade asked the students to pick benchmarks to compare fractions to. So these are cases where fractions, it's not easy. Well, that one would be, but these aren't easy to make into equivalent fractions where the denominators would be the same. This one is, so we could do that one pretty easily. But these ones, we're going to use this benchmark, and a popular benchmark that Engage New York uses is 1/2. Okay, so let's look at this first problem, thinking of a benchmark as 1/2. So I'm hoping you all see that 3/8 is less than 1/2. Right? 4/8 would be 1/2, so 3/8 is less than it. And this is greater than 1/2. Because 6/12 would be 1/2, so this is greater than 1/2. So then obviously that's got to be bigger. Isn't that interesting? That's how they do it. So 5 over 12 is less than 1/2. And then 7 over 8 is greater than 1/2. So this has got to be bigger. So that's what they talk about, these benchmarks. This benchmark would be 1. It says the benchmark is 1/2 and 1. Sometimes the benchmark can be 0. I'm going to see. Hold on. I don't know if it's annoying if I flip through. Oh, yeah. Do you see? Like, this is the directions. Give a brief explanation for answering referring to the benchmarks 0, 1/2, and 1. Right? So the directions are in there in Engaged New York, these benchmarks. All right. But anyway. So this one is easy because the benchmark is 1. This is an improper fraction, so this is greater than 1. This is a proper fraction, so this is less than 1. So there's my benchmark is 1. And then this one is a nice one because it's really easy to make those into equivalent fractions. If we multiply the bottom by 4, this would be 4 over 12. And then since now the denominators are the same, we just compare the numerators. All right, so let's look at this one. It says compare 2 over 9 and 1 over 4. All right, well, it says the directions, the hint that said make an equivalent fraction for 1 over 4 with the same numerator as 2 over 9. So 1 over 4, if we multiply top and bottom by 2, that's going to be 2/8. So now we're comparing 2 over 9 with 2 over 8. Ah, if the numerators are the same, then you just look at the denominator. The bigger the denominator, the smaller the piece. So 2 small pieces will be smaller than 2 larger pieces. So the 1/4 must be bigger. Isn't that interesting? I think that's cool. This says compare 3/5 and 5/12. Okay, so maybe you should use a benchmark of 1/2 for that. I feel like we did this one up there. Nope, well, it's pretty close. There's the 5/12. All right, so 3/5, use the benchmark of 1/2. This is greater than 1/2. And what was interesting when I looked at the answer key for this, they actually wrote this on Engaged New York. They said 2 and 1/2 over 5. It was really weird, would equal 1/2. This was in their answer key. 2 and 1/2 over 5 is 1/2. So 3 over 5 is greater than 1/2. And then they said 6 over 12 is equal to 1/2. So this is less than 1/2. So 3/5 is going to be greater than 5/12. Interesting. Very interesting. So if you needed some practice with benchmarks of 1/2, I just wrote a couple problems down. And then I highlighted these because these don't have 1/2 that we might need to make some notes on. So if we're trying to see if this is bigger than or less than 1/2, an equivalent fraction would be 4/8 to 1/2, so then you can see that that would be bigger. An equivalent fraction to 1/2 would be, if the denominator is 10, would be 5/10, right? So 7/8 or 7/10 would be bigger. And it's interesting how they write it in Engaged New York. They would have 3 and 1/2 over 7. Isn't that weird looking? Is equal to 1/2. And so this obviously is smaller. Oh, I should have put that over here, sorry. They would have had 3 and 1/2 over 7 here, and so this is bigger, or 3/7 is smaller. Okay, and let's see, I wanted to get all this done, but I don't think we're gonna. I'm going to try to limit this so that, we won't get it done. So it's not more than an hour. I don't want to, I know our class is an hour and a half, but I think I'm probably talking faster maybe, I'm not sure, but I thought an hour video would probably be long enough. All right, let's do these two and really understand it. So what I want you to see for these types of fractions is the number of parts you are away from 1. Okay? So do you see that this is 2 parts away from having a whole, and this is also 2 parts away from having a whole? But since these parts are smaller, this is closer to 1 because there's not as much missing to get to 1. So this will be bigger than 5/7. We're going to take some notes on it, but let's try it again. I'm hoping you'll see that these are each 1 part away from a whole. Since the eighths are a much smaller missing piece, this is closer to 1 than 4/5. So 7/8 is bigger. I mean, think about it. It's going to be a terrible drawing. I can do the eighths. So do you see that the missing part, and this is just how Engaged New York explains it to kids, but remember, kids have these really cool manipulatives. All right, so do you see that's missing a piece, and for fifths, I wish I had my manipulatives, 2, 3, 4, okay, pretend those are all equal, all right, and I'm going to shade in 4 of those parts. Okay, so do you see that the missing piece, or the Pac-Man mouth, is much bigger than that missing piece? So this is closer to 1 because the missing piece is small. So this is pretty common, a pretty common explanation in Engaged New York. So they look at the missing pieces. So if 2 fractions are missing the same number of pieces to get to the 1, if 2 fractions are each missing the same number of pieces to get to a whole, or a 1, a fraction with the smaller missing piece will be closer to the whole. This will be the fraction with the larger denominator. Because its pieces are smaller. Give me a minute to copy that down. So if 2 fractions are each missing the same number of pieces to get to the whole, the fraction with the smaller missing pieces will be closer to the whole. This will be the fraction with the larger denominator. So both of these are each missing 1 piece to get to the whole. Something that's been divided up into 22 pieces, the pieces are really small. So the 1 missing piece is going to be a very, very teeny piece. So this one is going to have just about the entire circle filled in. This is an Engaged New York way to compare fractions. I think it's cool, right? Fractions, I don't know what it is, but adult learners don't enjoy fractions. But if it was presented this way, with all of this number sense, I gotta say, I think it's really interesting. I'm wondering if the new group of learners that are coming up are going to have a nice hold on fraction sense. So here, we'll knock these off. We'll finish the rest of these. This one I think would be really easy to see if you just made an equivalent fraction, that these are the same fraction. This one, again, these are very easy to make into equivalent fractions, right? Multiply top and bottom by 2. We're going to be comparing 20 over 14 to 30 over 14, right? If you can make it into equivalent fractions easily, then that's a nice way to compare things. And then these are good because for some reason a lot of adults think if it's a fraction it's got to be small, but no, there's improper fractions. Improper fractions are bigger than 1. If it's a proper fraction, then it's smaller than 1. But if it's an improper fraction, it's bigger than 1. So we'll stop now. So we'll have quite a bit to do on Tuesday, especially so you can finish off your wow. But this is just the same stuff. I was just going to practice with some more 4th grade material. These are each 2 pieces away from the whole. We can practice with those. We can look at something, the benchmark of a half. So we'll start Tuesday practicing comparing fractions some more, and then we're going to look at least common factor, least common multiple, greatest common factor, and then there's one more sheet that we'll finish off on Tuesday. Okay? I think probably an hour-long video is plenty. All right. So anyway, there is an oh wow, but don't panic about it because we haven't done a big chunk of it. We haven't done a big chunk of it, so hopefully we'll be able to get that done on Tuesday. But we'll see. We're not going to push it too much. But after today, we don't have many lessons left and not many videos left. So we're really coming down the home stretch. After section 2.2, we just have a section on adding and subtracting fractions, which is very, very short, and then we're going to hit multiplying and dividing fractions a little harder. So we don't have a lot left. So that's good. So Zoom me if you have any questions. I will get those tests done. I'm working really hard on them. I had a bunch of other in the queue, so I'm going to keep plowing through those. And I will see you soon. I hope everyone's doing well. And please, again, let me know if you have any questions. You can contact me with Zoom. You know how easy it is now. You just have to send me a message through Remind that you want to Zoom. All right, take care. And we can say this now, have a good weekend.